This video is about the implementation of our Lambda loop as a feed antenna in a radio telescope. And we will estimate the gain and beamwidth of the parabolic antenna. We are flying to the Starkenburg Observatory near Heppenheim in Germany. The location is on a hill, shielding the observatory from disturbing light and radio wave sources of the civilization. Look at this beautiful area. The observatory is a non-profit organization. Anyone interested can join. Just take a look at the website. There are great things to discover, also for kids and teens. This building is the Radio Astronomers domain. Underneath this weather protection, also called radome, is the parabolic antenna that we will talk about. The amateur radio astronomers built a new feed antenna for it, using the loop antenna that we explained in detail on Electronics Unmasked. In the last episode, we were briefly explaining the radio telescope's principle, and we computed the radiation diagram of the new feed antenna. In addition, we talked about the effects of noise and intermodulation in that context. An SDR receiver experiment was showing that the setup with the loop antenna is less sensitive to interference. The frequency selectivity of the loop protects the low noise preamplifier from strong signals on the neighboring bands. I really have to say that the 1420 MHz loop in the cooking pot is built very well. The reflection measurements are showing a perfect impedance matching. Congratulations, you did everything right. I'm guessing you carefully watched all our previous videos about the antenna. The bottom of the aluminum pot is a reflector, and the sidewall is shielding signals coming in perpendicular to the main beam direction. The resulting radiation pattern is pretty well suited to feed a 3-meter parabolic antenna. By the way, the fry pan, yes, it is really an aluminum frying pan, is further reducing side lobes. The expert would call this a corrugated horn. "We're just doing it," is the motto of the observatory. Great, isn't it? This is what the installed antenna looks like under the radome. Next, let me show you how to calculate directivity, gain and beamwidth of the main loop. A parabolic antenna's effective area equals approximately its aperture A, as long as it is much bigger than the wavelength. The gain is calculated by A divided by the effective area of the so-called isotropic antenna. This relation applies in general. We already talked about it in an earlier video about helpful formulas for RF and EMF. In our case, the aperture is circular, so the area A equals pi times d squared divided by 4. Just as a reminder, 10 times the logarithm of g yields the antenna gain in dBi. In our case, the resulting gain factor is 2014, corresponding to 33 dBi. With a vertical and horizontal 3 dB beamwidth of 4.53 degrees, our little antenna tool calculates 33 dBi antenna directivity, which we must consider here strictly speaking. Gain equals directivity times efficiency, which we estimate to be 90% here. So the actual gain will be 32.58 dBi. It's important to know that the parabolic antenna receives signals outside the 3 dB beamwidth according to its radiation diagram. And this effect sometimes needs to be taken into account. The sketch is simplified. It looks as if the exact sector of the sky is seen by the antenna. The spatial angle of the total sky is 360 × 180 degrees. divided by 4.53 degrees squared yields about 3158 sectors, being the resolution to create radio images. Here is a rule of thumb in case you want to estimate other parabolic antennas or radio telescopes. The beamwidth is approximately 58 degrees times the wavelength divided by the diameter. In the lab under the antenna there is control units, the SDR receiver and a PC with software. The amateur radio astronomers are working with the program EasySky and SDR receiver software. There is a number of videos on YouTube explaining that. I will give you some links under the video. I think it's a really nice and interesting techie hobby. Here is an example of a received signal that looks like noise at a first glance. You can barely see a maximum at 1420 MHz. After the fast Fourier transformation, however, we can see the desired hydrogen signal clearly. The narrow peaks are not signals from space, they are man-made. Well, that happens with sensitive receivers when there is an interference source nearby. It turned out that a display in the lab was the root cause. The experimenters found that out and simply switched off the device. But anyway, in order to avoid this, they need to find out how the interference signal enters the system. Maybe we will come back to that later. In the case you had interference caused by neighboring radio services, this would be not so easy to solve. In a coming episode, we will make use of our computations on radiation patterns and side lobes on the neighboring frequency bands to investigate potential interferers. In other words, we want to investigate from what distance radio services could interfere with the reception of the radio telescope. The Lambda loop antenna seems to have an advantage for radio astronomy. The amateur astronomers will certainly have a lot of fun with the new system, and we are excited to see new measurements. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.